Okay, so it's 5 o'clock here in a cold, miserable March day in the UK. So good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast. And good evening to anyone joining us from Europe or stations further east. Thank you for joining this, the 21st of our regular series of seminars on pumping topics. 21. We've come of age. And you guys seem to be aware that what we're doing these days. We had over 500 registrations for today's courses, the two courses today, 293 this morning, 229 this afternoon. So I think we've arrived, and I'm wearing a snazzy new waistcoat just to celebrate it. Anyway, this presentation will last about 35 to 40 minutes. Allowing us time for a Q&A session after the presentation. So let me start the screen share again. And here we go. So here is a listing of the previous short courses we've run during the last year. If you've missed any of them, you can get a copy of the materials from our website using the following link, shortcourses.rawpumpen.com. Or you can go to rawpumpen.com and follow the link to RP Short Courses. If you go to rawpumpen.com, you get to this screen. And here is the link to the RP Short Courses. If you click on that, it takes you to this screen, which you can also access directly using that link. But here you will see all the courses listed, and you can click on any of them to see the course material. Most of the 20 courses are up there, I think 18 so far. We don't like to put them up too soon after the live presentations, or people will not bother to attend and just download them later. This spoils the value of a live Q&A session, which is actually my favorite part of these sessions. Well, here is what we'll be covering today. BB4 pumps with a particular emphasis on the power market, boiler feed pumps. But they're also used extensively in the desalination market, and I plan a future session on that market. As usual, we'll be holding a Q&A session at the end. So please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the session, and the rest will address by mail in the coming days. We are recording this session and will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and the Q&A summary from both of today's sessions. BB4 pumps, described in API 610 as single case, multi-stage, radially split case pumps. But they're also popularly known as ring section pumps, segmental ring pumps, and tie rod pumps. Here's a photo from a recent order, and you can clearly see why it's called a ring section pump or a tie bolt design. Before I look at the design of these pumps in detail, I want to talk first about the industry in which they are so prevalent, the power industry, as boiler feed pumps, particularly combined cycle power plants. When you understand the market they're going in, you'll better understand the design features we've built into them and why. In a single cycle gas plant, a gas turbine burns natural gas and drives a generator to produce electricity. The hot exhaust gases go to waste. There's no waste heat boiler, so no boiler feed water pumps. In a combined cycle power plant, a gas turbine generator generates electricity and the waste heat is used to make steam to generate additional electricity via a steam turbine. And this last step enhances the efficiency of the electricity generation no end. In a combined cycle power plant, the exhaust gases go to the heat recovery steam generators, which are fed by boiler feed water pumps. And generated steam goes to the high pressure and low pressure steam turbines, which generate additional power. The exhaust steam is condensed and goes round the circuit again. Note the high pressure and low pressure steam circuits are fed by the same pump. Now we'll cover that later. Here it is schematically. Air and natural gas go into the gas turbine, which generates electricity. The exhaust gases go to the heat recovery steam generator. High pressure water goes in, steam comes out to the steam turbines, which generate more electricity. Well, that's it in a nutshell. Combined cycle gas plants are increasing in popularity. They're more efficient than coal-fired plants. Modularized plants are available almost off the shelf and are considerably cheaper than coal-fired plants. And they're politically popular in times when the world is looking at reduced emissions. I'm not going to play this video now, but here is a link to a short video which runs for about 3 minutes and gives you a good overview of combined cycle power plants. So what is a boiler feed pump? It's a high pressure, multi-stage pump that runs continuously to pump feed water to the heat recovery steam generator. Usually it will be a BB4 pump, as we're describing in this presentation. Can be a BB5 pump, which is a double case barrel pump, you'll remember. And this may be specified by some customers, particularly oil and gas companies like Shell, Exxon, or Linde. Traditionally, on baseload plants, the feed water pumps run continuously with few starts and stops. But increasingly nowadays, gas-fired power stations are used as peak shavers alongside renewable energy plants. And so they're seeing far more frequent stops and starts and thermal cycling. This is a more exacting requirement for the pumps to be designed to withstand. Normal material of construction is C6 due to strength and corrosion resistance, but as you see, they're also available in other materials. It's not a difficult or exacting sealing proposition, so normally a single seal with a Plan 23 flush piping is used. Plan 23, you'll remember, is continuous recirculation from the seal chamber through a heat exchanger back to the seal chamber. What is the key evaluation factor for boiler feed water pumps? Efficiency, every time. Better efficiency equals more electricity equals higher profit. Efficiency and life cycle cost will frequently be more important than the capital cost of the equipment. So efficiency is most critical. But I want you to think about two different concepts of efficiency. High initial efficiency and high sustainable efficiency. Let me illustrate this by an example. I'm going to show you two different pump selections. The first one has a higher specific speed, higher number of stages, 13 in this instance, and a longer, skinnier shaft. Efficiency 81.7%. The second has a lower specific speed, fewer stages, 8 in this instance, shorter, more rigid shaft, and apparently a lower efficiency of 78.7%. Which one do you buy? Well, if you're an EPC with a lump sum turnkey contract, it's a no-brainer. You buy option 1. If you're an end user or a consultant looking for the best long-term solution, you'd be wise to say, hold on a minute, let's look at this a bit more. So let's look at it a little deeper. Here on the left is the high specific speed rotor. It has a longer shaft span between bearings, skinnier shaft, more shaft deflection or sag when at rest, and more likely for the wearing faces to touch during startup or rundown. It's reliant on the Lomakin effect to effectively reduce the effect of the shaft sag. Lomakin effect? I'll come to that in a minute. Here on the right is the low specific speed rotor. Shorter bearing span, bigger diameter, stiffer shaft, less sag, less dependent on the Lomakin effect. It's what they call a non-contacting rotor, and this is a term you will see in specifications. So what the hell is the Lomakin effect? It's another of those terms, like Bernoulli, that has pump people looking wise and nodding sagely. Meanwhile, others with less theoretical knowledge say, what? Well, here it is in a very simplified form. If you're a rotating equipment engineer, then you ought to read up on this and Bernoulli while you're at it. But this will do for most of us generalists. In any wearing or bushing with differential pressure, there'll be axial flow passing through the clearance. If the rotating part moves away from the center of the stationary part, there'll be different clearances on each side. So when you get sag, you've got bigger clearance at the top, smaller clearance at the bottom. The side with the greater clearance will pass more flow than the side with the tighter clearance. More flow passing through the clearance will result in locally a higher velocity, and hence the effective local pressure will be lower. So you're going to have lower pressure at the higher part of the rotor. Now this effect tends to be stabilizing. The force of the lower pressure on the side with a larger clearance, at the top in other words, and higher pressure on the side with a tighter clearance at the bottom, make the rotating part want to move back towards the center. In effect, the wearing or bushing becomes a stable bearing. This reduces the chance of rub even with a flexible rotor, but not at startup and rundown. This is when wearings and bushings might touch. Here's the importance of the stiff shaft, non-contacting design. There's a lot to take in here, so we'll take it steady. Here we have a plot of pump efficiency on the left against pump running hours. In dark blue, we have option 1 pump with the long, slender shaft with longer bearing span, higher mass of components, you've got more impellers, and larger shaft deflections, more sag. In pale blue, we have the option 2 selection with the shorter shaft length, shorter bearing span, reduced mass of components, you've got fewer impellers, and a larger basic shaft diameter. With option 1, we see that the efficiency starts higher, but falls off quickly as wear occurs. With option 2, the stiff shaft pump, wear is far slower, and so the efficiency benefit quickly catches up and overtakes the option 1 pump. The mean time between overhauls is over 2.5 times longer in this example, hence high sustainable efficiency. Here we see a Duncan and Hood diagram. It's an industry standard, not just a Rohrpumpen thing. The K factor is what you need to be looking at. The lower the K factor, the stiffer the rotor, and the lower the shaft deflections, lower the sag. The blue line in this diagram is the minimum design line for wet running pumps, where the Lomakin effect is taken into account. The red line is for dry running pumps with no benefit from Lomakin effect taken into account. The purple dot is the option 1 pump, only just in the acceptable range. The green dot is the option 2 pump, comfortably in the safe area where you want it to be. Again, to reiterate, the lower the K factor, the stiffer the rotor, and lower the shaft deflections. Hence, a non-contacting rotor is what we're looking for. Well, that's the difficult bit over. Let's move on to the pump design and features. Firstly, what does API 610 say? Well, a BB4 pump is not fully compliant with API 610. Well, this is generally fine as we're pumping hot water, not hazardous hot hydrocarbons. Most specifiers don't require API 610 compliance for boiler feed water pumps. So we start with a build that is fit for purpose and still gives you a high quality pump without unnecessary and costly features. Here on the left is the standard build. Now, we'll look at these in the coming slides, but we recognize that the power plant might be going on a refinery, and so API 610 and oil company specs might well be imposed. And many of you specifiers are so used to specifying API 610 that you may do so on autopilot. So here on the right are the things we may need to incorporate to meet API 610 as closely as possible, bearing in mind that by definition, full compliance is not possible. Again, we'll look at all of these in the coming slides. Well, this is the Rohrpumpen model GP pump for boiler feed water service. It's based on our market-leading BB5 pump hydraulics, our barrel pump hydraulics. It's a ring section pump, tie bolt design, here centerline mount, and here shown with an interstage takeoff, a low pressure takeoff. The hydraulic design, well, it's designed for 2-pole, 50 or 60 hertz. It's not a high-speed pump. We have high and low flow impellers available for each pump size, which is good for retrofits and re-rates for duty changes in the future. We have low NPSH first stages available, and we have designs for interstage takeoffs. The hydraulics have been and continue to be optimized by CFD, computational fluid dynamics, to maximize the efficiency. And this is an ongoing, continuous improvement. Here is the range chart at 50 hertz, so flows up to 1200 cubic meters an hour and heads to about 2000 meters, 200 bar. Or at 60 hertz, flows up to 6,600 gallons a minute and heads up to 10,000 feet, not 1,000 feet, 10,000 feet. We have 3 mechanical design standards, and each can be upgraded to the next level. You can pick and choose features that you want without necessarily going the full API route. This is what the pump looks like in section. You can see the inline stacked impellers, the diffusers or ring section construction, the tie bolts holding them together, and the balance line between seal chambers. The thrust balancing device. Here we're showing the balance disc. Balance drum is an option. It's centerline mount, and the flange ratings, 600 pound, 900 pound, 1500 pound, or 2500 pounds. So that's around 350 bar, 5000 PSI in C6 construction. Suction side is good for about 50 bar in C6 again. Confined O-rings sealing each stage. So we have metal to metal finish, metal to metal, face to face with confined O-rings. Various materials of O-rings according to service, maybe NBR, acrylonitrile butadiene rubber, or EPM, ethylene propylene rubber, EPDM, ethylene propylene diene monomer rubber. They're the most common ones, I think, those three, but at higher temperatures, FKM, fluorocarbon rubber, FEPM, tetrafluoroethylene propylene, or FFKM, perfluoro rubber, and these are more expensive. We have an optimized inlet channel to ensure good flow into the impeller, and you saw this in the earlier slide on suction chamber CFD design there. We have investment casting impellers, which optimizes the efficiency and the repeatability. Shafts, impellers, and complete rotors are balanced to ISO 1940 G2.5. We have high and low flow hydraulic versions of each pump size. And this is important, as I've said a few minutes ago, for retrofits and re-rates and for interstage takeoffs, which we'll come to in a few minutes. Impeller mounting and shaft. We have two designs, one with a straight shaft and the sleeves securing each impeller. This is used on the smaller, lower pressure pumps. The second version is the API version with stepped shaft and impellers individually secured by split rings. This is used on larger, higher pressure pumps and whenever API 610 is specified. The wear rings. Well, the base design case is case wear rings only, no impeller wear rings. We run with closer clearances than API for optimum efficiency. Impeller wear rings can be fitted later as wear occurs. At the first service, for example, you can machine the impellers to take wear rings at that stage. With peak wear rings, shown here in black, the clearances can be closer, or closer still, and the efficiency improved. But you can also have replaceable wear rings, case and impeller, installed from the outset. This is the API option. Here in blue is the case wear ring, and in gold, that's showing the impeller wear ring. Or you can have a combination of the two. Here, a peak case wear ring and metallic impeller wear ring. Here is the bearing housing. It's a 360-degree one, rather than the 180-degree one that some of the older pumps in the industry you might find. Has vertical fins to provide optimal cooling. Here you see the radial bearing. It's a single row cylinder roller, anti-friction bearing with splash oil lube and a constant level oiler. And we have an in-pro bearing isolator. If you choose, or if you need, the option of a tilting pad, hydrodynamic or Kingsbury bearing, you'll need a force feed lube system, in which case we have available this shaft-driven main oil pump to replace this assembly. So that brings us neatly to hydraulic balancing, thrust balancing. With a BB4 pump, you have stacked impellers, all facing the same way. So the thrust builds up and is more than a conventional thrust bearing, a ball bearing can take. So there are several ways of handling this thrust. You can have opposed impellers, 5 facing one way, 5 facing the other, thus equalizing the thrust. This is commonly done on BB3 and BB5 pumps. But on BB4 pumps, we use either a balanced disc or a balanced drum. Here is the balanced disc. You have full discharge pressure acting on one side and suction pressure acting on the other side because of the balance line back to suction. The pressure, the thrust, is broken down by close axial clearance between the two faces. It balances out 100% of the thrust, so no thrust bearing is required, just a radial bearing. A little clearer in this slide, suction pressure this side, discharge pressure this side, the pressure breakdown across this face. And the close clearances, though, mean it is only suitable for clean fluids, so it's ideal for boiler feed water pumps. API 610 is written with process fluids in mind, which frequently contain solids, and this design is unsuitable for that. So that's why API 610 has a blanket ban on balance discs. Here in this sectional, you can see the balance disc. And here you see the balance line, which means you have suction pressure here, of course, the suction side of it, but also here on the discharge end. With the close clearances, there is risk of the faces touching and wearing prematurely, especially during frequent startups and shutdowns. So there's an option of a lift-off device comprising a preloaded spring and an angular contact bearing to ensure that the thrust disc faces are held open during startup and rundown. And this is an option which many manufacturers offer. Here is the alternative thrust balancing mechanism, the balance drum. And this is required for API 610 pumps and whenever there are solids in the pump fluid. Thrust is broken down in the radial direction. It has greater clearances because of the solids handling capability. And so with those greater clearances, it only breaks down 85 to 90% of the thrust. So you need a thrust bearing as well. Here we see we've got discharge pressure this side, suction pressure this side, and here is the breakdown of the pressure. It's not as efficient as the disc, but it is better for solids handling. We have several bearing combinations according to needs and preferences. Here is the simplest and least expensive, used with the balance disc. No residual axial thrust to balance, only radial loads, the weight of the rotor. So it's a simple ring oil lubricated roller bearing. If you prefer, on larger sizes particularly, a hydrodynamic bearing, a sleeve bearing, again, ring oil lubricated. With the balanced drum, you have residual thrust to accommodate. It only balances 85 to 90% of the thrust. So you need an angular contact thrust bearing. Ring oil lubricated will do the trick to take that residual thrust. On larger pumps with higher residual thrusts, or when specified by the customer, you can have a hydrodynamic tilting pad, Kingsbury type bearing. And this will require a force feed lube oil system, perhaps to API 610 or maybe API 614. The nuts on the tie bolt need to be tightened to the correct torque. On smaller pumps, a torque wrench will do this job. On larger pumps, tightening the tie rods nuts can be an issue. You may need a hydraulic nut tensioner, which is a big, expensive piece of equipment. But there is an alternative, multi-jack bolt tensioning. This is just the coolest thing I ever saw, multi-jack bolt tensioning. It's widely called super bolts, although that is actually the trade name of Nordlock. Other manufacturers of multi-jack bolt tensioning exist. It allows you to tighten the bolt or tighten the nut using conventional hand tools instead of requiring a hydraulic bolt tensioning tool. You tighten the nut by tightening each of the 6 jack bolts in turn using conventional hand tools. Or you can buy a super bolt tool to make it even easier. Tightens all 6 of them together. Let's look now at the Interstage takeoff. Now, you may recall back at the beginning of this presentation, I showed you this process schematic. It shows the boiler feed water pump feeding both the high pressure steam drum and the low pressure steam drum. Well, here is how that is achieved. An intermediate pressure takeoff at the appropriate stage of the pump. It means that the impellers of the first few stages are designed for the full flow, and after the takeoff, they're designed for the reduced flow. And this is one reason why we have several impeller hydraulic designs for each pump size. So who makes BB4 pumps of this type? Well, you know that Rohrpumpen makes them. I told you that already. Who else are the big players in this field? Well, in this market, the heavy-duty, high-pressure pumps, these are the main players. Rohrpumpen, Sulzer, Flowserve, KSB, SPX, Torishima, and Ibara. And finally, for today, be aware there are many pumps other than boiler feed water pumps on a power station, and we can help you with all of them. Condensate pumps, cooling water circulation pumps, or the boiler feed water pumps, of course, utility pumps, and fire pumps. Here are a range of vertical pumps. This one, an important one, condensate pumps. You will almost always need a vertical, a VS6 pump, because you have boiling water, 0 NPSH. Here on the right is a BB3 pump. These are sometimes specified by customers instead of BB4s as the boiler feed water pumps. General service pumps, fire water pumps. And we can also help you with packaging of pumps into skids or modules. Well, that pretty much concludes the fun for today. Here is where I get to advertise the next of the short courses. Decoking. Technically, a very interesting specialist field, and one of which Rohrpumpen is a market leader. It's going to be a very interesting session, and I think you'll love it. Thursday, the 30th of March. So that's 3 weeks' time. After that, we'll look at pumps for the desalination market. And after that, magnetic drives for the chemical process and API industries, and cryogenic pumps. I'm leaving this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer will be answered within a few days. Anything you think of later, email to info@shortcourses.ropumpen.com. Our marketing team are standing by to direct your questions or suggestions to the best person to answer them, and they'll be sending you the YouTube recording and the PDF of the presentation. If you need a certificate of completion for this short course, again, info@shortcourses.ropumpen.com. And here, right at the end of the presentation, are 8 slides that remind you of who we are and what you do. They'll be in the PDF copy of the presentation you get, so you can peruse them at your leisure. I won't bother you with them right now. We'll get on with the important bit, which is the Q&A. So let's look and see what we've got in the way of questions. Here we have one from the anonymous attendee who says, can you give a rule of thumb on cost differential between API 610 and the non-API pump? It will depend which, it's almost like a shopping list. You build it up from a real base pump to whatever it is you need, but it could easily be 25–30% difference in price, but it will depend which options it is that you would like to see. Gerard Nagel says, slide 28, I haven't seen those type of pump curves before. What do the vertical black lines mean? So let's have a look at slide 28. Okay, this is just the area bound curves, the sometimes called tombstone curves. And what we are looking at here is the black lines here with arrows that's showing the best efficiency point with a full diameter impeller for each one. So you can see where the best efficiency point is. Of course, what we would get, that's just the area bound curves to show you the range. You would actually get a specific pump curve for your particular duty. Yeah, another anonymous attendee has said, do I need to be concerned with Lomakin effect on every pump? If not, when? Is Lomakin effect specific to BB4 or also apply to centrifugal pumps? Good questions. Lomakin effect would also on any multi-stage pump, so a BB3 pump or a BB5 pump. It's worth considering because some people might give you a long skinny shaft pump that is of questionable suitability for the duty. You pays your money, you takes your choice. You can buy a cheap and cheerful pump that might have short life or short mean time between overhauls, or you can have a more rigid, rugged design that will last longer between overhauls, but you'd be paying more for it. And that was the purpose of the illustrations I gave with option 1 selection, option 2 selection. Option 1 selection will be cheap initial cost, higher long-term cost, because it'll be in the repair center more frequently than will the more expensive stiff shaft construction pump. Martin Della Torre says, are there any chance of pump rings differential radial displacement due to vibration and possible metal-to-metal contact with rotating parts? That is what we're concerned with frequent starts and stops as the on a skinny shaft pump, there's the possibility of that it could be touching or at least wearing more quickly than it would do otherwise. That is the concern, and that's why we pushed you towards buying a slightly more expensive pump that has non-contacting rotor, a non-contacting rotor, a stiffer shaft construction, low K factor. Roberto Carmona says, I've worked with both ring section pumps placed inside a drum and those operating with only tie rods in boiler feed water service. Any comments on why one would be encased whereas others are not? What you've described as the ring section pump in a drum is in fact a double case pump. So it's a BB5, and yes, that's for higher pressures. Higher pressure solutions. Paul Berthiaume says, what percentage of your orders specify a suction transient test for boiler feed pump applications? That's not a question I can answer right now. I'll get you an answer, and you'll get a written answer in a few days' time. S. Suratan says, hi, is this pump available for low flow, high pressure applications, e.g. 9 kilograms per hour at 150 bar, presumably? Yes, and if you'd like to speak to your local raw pump and salesman or your KSB salesman, we try to be neutral in this, or the FlowServe one, or even the Gould's one. Yes, that you would be able to find this type of pump for that sort of duty, and speak to your salesman and he'll be able to give you a good selection. Kevin Rowe says, will a mechanical seal or stuffing box give better performance on a boiler feed pump, multi-stage pump? You could have a stuffing box, a packed gland. They're not very common these days. People do tend to use mechanical seals on it. I think the worry might be high temperature steam escaping through the packing rings. If the packing rings loosened, you could get you could almost get a jet of hot water, perhaps. David Powell says, in your opinion, is there any significant benefit in BB3 versus BB4 for the service? BB3s are more expensive. They do have, because you've got back-to-back impellers, or 5 impellers facing one way, 5 impellers facing the other way, you've got balanced thrust. They'll probably last long. Where BB3s are really used, they're pipeline pumps. That's their that's what they were designed for lasting forever in lousy conditions out in the middle of nowhere. They're possibly over-specified for boiler feed water service. You'll pay more for them, maybe a little more reliable. BB4 does the trick for what is really a not overly difficult pumping situation. Anonymous attendee has said, what are the pros and cons for BB3 versus BB4 for boiler feed water service? Well, yeah, I kind of answered that. I'll give a more considered answer in writing. That was my first off-the-cuff response, but I can give a more detailed response. Anonymous attendee again, how sensitive is this pump to dirt and to high temperatures? Well, dirt, as long as you haven't got, if you've got dirt in the pumpage, then you must use the thrust balanced drum construction, not the balanced disc one. Otherwise, it's like any pump. They don't really like dirt. They will wear out if you've got dirt in them. Nathan Little has said, what's the benefit of using peak with a wearing rather than without a wearing? Well, peak would have to be as a wearing that is installed in the pump. We couldn't just spray it on, I think, the pump surface. So you would need a wear surface, a mating wear surface. But let's see, you'd have the peak wearing on the casing, and the impeller could either have a wearing or have an integral wearing. Now, to me, there's no real disadvantage to having the no impeller wearing, an integral impeller wearing. I mean, what happens after about 2 years? You decide that pump, the efficiency has started to drop. You think the clearances have opened a little, so you take it out. You machine all the wearings, all the impellers to fit wearings later. Now, if you'd had impeller wearings on them, you'd have to machine them off anyway to put new wearings on. So there's no real advantage to having wearings from the outset. But API requires it, many specs require it, so it's an available option. But we don't have it as the base option because we're trying to save you money for unnecessary expense. Anonymous attendee, is C6 metallurgy suitable for boiler feed water streams that may have been chemically treated? Is 316 SS metallurgy available? Yes, it is. So is D1 and D2 if you've got if you've got worries. A8 316 is not nearly as strong as C6 or as D1 and D2. So we have to look at the pressure ratings in that circumstance. Erkument Yeltsin, excuse me if I pronounced it wrong. Initial efficiency versus sustainable efficiency. Calculation, cost calculation, please. Well, that's what you need to be doing. You need to be comparing two pumps. You need to look at their initial efficiency. And you need to consider the K factor to see whether or not you're going to get fast degradation of that efficiency. It's not something I can just give you a calculation for. Erkument Yeltsin, long-term sustainable efficiency will be better, you said, but we have to prove it with figures. Yes, you do. You need to put the pump vendor on the spot to get him to justify his figures. Anonymous attendee has said, is it possible to retrofit the option 1 pump with the option 2 pump, or not economical and a pump replacement is the recommendation? It will be extremely unlikely to be able to fit a stiff rotor inside an existing casing that's designed for skinny rotors. You'd be replacing the whole pump. Anonymous attendee says, are allowable nozzle forces significantly lower than API 610 guidelines? No, we follow API 610 guidelines for those. Anonymous attendee again, for the high pressure versus low pressure BB4, is a booster pump typically used or not? It might be that you need an NPSH booster if you had low NPSH, yes. Anonymous attendee says, have BB4 pumps been used in supercritical CO2 applications? I'd have to pass on that question and seek more expert advice. Okay, Nathan Little has clarified his earlier question, which was about peak wearings mating against a wearing versus against the impeller. And the answer is, I think I said, that's what I said before, there's no real difference. If you've got a peak wearing mating against the wearing surface that is integral with the impeller, you've got the same clearance, the same wear rate will occur as it would do if you had a wearing, a metallic wearing in there. So what's the difference when you take it to overhaul? none whatever. You would have, with the integral wearing, you'd have to machine away that material and fit a wearing. If you've already got a wearing which is worn, you have to machine it away to fit a new wearing on it. Paul Bertillon says, what are your thoughts on specifying API clearances with the pump order rather than allowing the OEM to use tighter clearances to meet performance, because the clearances will open up after a few starts and stops to API levels anyway? Yes and no. It won't be just a few starts and stops that will cause it to open up. And let's face it, the API ones are going to continue to open up as well. So again, you want to put the pump vendor on the spot and say, prove to me the reliability and the sustainability of your wearing clearances. It's a valid question to ask them on each specific case. They say, okay, you're promising me 82% efficiency now. What's it going to be in a year's time? You know, put him on the spot. Okay. That appears to be all the questions at the moment. Looks like there were about 23 questions there, so that's good. So let me close that. And let me say thank you for attending today. I've enjoyed preparing and presenting it. I hope you found it useful. I look forward to seeing you on the 30th of March for the next session on coking pumps. Now it's coming up to 6 o'clock here in the UK, which means it's beer o'clock as far as I'm concerned. And I'll say goodbye and thanks very much for attending. Bye-bye.